and things were kind of different. So machine learning, it certainly existed as a field, but it was a little bit niche back at that time, and there was really no conversation happening between machine learning and theoretical computer science for the most part in the 90s. Certainly, as you've heard, no one would be caught dead saying that they worked on neural networks, for example. On the optimization side, and that's sort of why I went to grad school at Cornell to study combinatorial optimization, approximation algorithms were really big, okay, as they are now. They already were in the late 90s. Parts of submodular optimization were big. Specifically, that's when the first combinatorial algorithms for minimizing submodular functions, exactly in polynomial time, were coming out. But actually, nobody was working on approximation algorithms for submodular optimization problems. And at least the sense I got from my grad courses at that time is the reason because that was some dusty old field where people figured out the interesting stuff in the 70s. And that's all kind of ironic because now fast forward to 2019 and sort of approximation algorithms for submodular optimization problems have been really big in both theoretical computer science and machine learning over the past sort of 10 to 12 years. And speaking about machine learning, another thing that I find amusing, so you hear in the newspapers about machine learning eating the world or whatever, and people are usually talking about sort of technology when they're discussing that, but it's kind of happening in academia as well. So both of these papers were published in machine learning conferences, Colt and NeurIPS. The second one even was a full oral presentation at NeurIPS, despite the fact, as you'll see, these are really kind of theoretical computer science, kind of pure approximation algorithms papers. All right. So I've already mentioned the word submodular a bunch of times, so let's just make sure we're all on the same page. So what's a submodular function? So for most of the talk, I'm going to be talking about set functions. I'll generalize this a little bit at the end if I have time. So there's some finite ground set or universe, and we have a real valued set function f. And submodular is just the natural definition of diminishing returns, okay? Meaning that the marginal value you get by adding some element of the ground set to a set that doesn't contain it, it's bigger if you add it to a small set compared to the marginal value if you added it to the big set. So the more stuff you already have, the less your marginal value for any one thing that you don't have. Okay? So that's the definition of submodularity. Hopefully, many of you have seen this at least once in your life. Okay? So I talk about diminishing returns, so it makes it sound like an analog of a concave function for set functions. And sort of it is, but it also kind of exhibits some characteristics of convex functions as well. So like I mentioned at the beginning, it's actually minimization of submodular functions, which is polytime solvable, and maximization is what's hard. So submodular functions, they're sort of a sweet spot. On the one hand, you can use them to express a decent number of different applications. On the other hand, they have enough structure. You can prove strong algorithmic bounds for them. On the other hand, the structure is sort of idiosyncratic. Okay, it's kind of this weird hybrid of convex and concavity and convexity. Okay, so that's a submodular function. What are some examples? So one, if you're just going to keep one concrete example of a submodular function in mind today, I'd recommend maybe the cut function of a graph. Okay? So for example, for an undirected graph, so the universe here is going to be the vertices of some undirected graph. And for a given subset, oh, does this not show up on the screen? I see.
Fetch the data.
Yeah, sounds good. Easy to reach at least, right? So for a given subset, so it'd be a subset of vertices, you look at the boundary. So you look at how many edges have one endpoint in each of S and V minus S. In this case, it would be 4. And that's the value of the set function on this set. Okay, just the number of edges sticking out of that set. Easy to verify that that's submodular. Let me just also point out that's a non-monotone function. Okay, at no point did I promise that these functions are monotone or even non-negative. So in particular, if S is the empty set, nothing sticking out of the empty set. If it's the whole set, nothing sticking out of the whole set either. Okay, so it's 0 on the two endpoints and positive in between. There's other examples too. So like an example of a monotone submodular function would be a coverage function. So here elements in the ground set would correspond to subsets of some other set. And the value, and so if so a subset would be then sort of the union of some subcollection of these sets, and the value of the function would just be how much you cover. You could think, just sort of for a prosaic example, you could imagine you were hiring a team of people. Okay, so there's some number of skills you wanted to make sure you had covered. A given person may cover more than one skill, and so you want to hire people so that all the skills are covered. Okay, and maybe there's even a cost of doing so. This will now make it a non-monotone function. If for each person you hire, you subtract something away from the objective function. Okay, so that's another nice example of a non-monotone submodular function. Take a monotone one and subtract a modular or an additive function. Okay. And there are various other examples as well. This being a theory seminar, I'm not going to dive sort of too deeply into the applications, but like I said, a lot of people in theoretical computer science and machine learning have been thinking about these functions for the past 10 to 15 years or so. Okay, so what's this talk going to be about? For most of it, I want to focus on a very basic question in submodular optimization, which is just, I give you a submodular function, and I want you to maximize it. Or failing that, at least to maximize it approximately. Okay, so there are no constraints, so the feasible solutions are just all subsets of the given universe. Okay? Now when I say given, you're given a submodular function, right? It's sort of a set function that has an exponential number of values encoded in it, so I have to tell you the representation. You can do it different ways. For today, to keep it simple, let's just look at the black box model, also called the value oracle model. So the only way you can learn about the submodular function f is by querying it at different points. Okay, that's called a value query. And we're interested in algorithms that query it only a polynomial number of times. And the question then is, for such an algorithm, how close can you get to the maximizer of the submodular function? This, of course, would be a trivial problem if f was monotone. You'd just take everything. So needless to say, we're talking about non-monotone submodular functions. Okay? As I mentioned, canonical examples of submodular functions are cut functions. So one special case of USM, unconstrained submodular maximization, would be max cut in graphs. Another one would be the max directed cut in directed graphs. Okay? As I'm sure some of you know, these two specific versions, they have enough structure you can write down semi-definite programs, relaxations for them, and round them and get pretty good approximations, better than 4/5, for example, for both of these problems. And you could ask, to what extent is that true more generally? If the only thing I tell you about a function is that it's submodular, not necessarily a cut function, can you also do very well? And there are limitations on how well you can do with the general problem. So Feiga, Marachny, and Vondrak proved that information theoretically in the black box model, you can't hope to get close to what you can get for the cut problems. You can only hope to get a 1/2 approximation using a polynomial number of value queries. Okay? So for the abstract USM problem, that's kind of the line in the sand. That would be the holy grail, to get a 1/2 approximation using a polynomial number of value queries. Okay? Any questions so far? Yep.
What happens if you do this over some other lattice that's not a Boolean lattice? I mean, you guys only care about Boolean.
Yeah, so I mean, if there's time at the end of the talk, I'll talk about one other lattice, which is just really, basically optimizing a continuous function over the hypercube for the max and min notions of join and meet. Okay. As far as a generic result, I'm unaware of any kind of, very generic positive result.
Metroid or something, I don't,
Let me think about that. So, yeah. So you're saying over the lattice
like
of...
I don't know, Metroid or something, can you... Are there other interesting cases than just the Boolean?
Oh, okay. That's a good comment. So surely. So as you say, submodularity makes sense over any lattice. Yeah. And for most of this talk, I'm going to focus on just one. People do think about it over other lattices. Yeah. I'll do it a little bit at the end of time, but obviously other lattices would be interesting as well.
Uh-huh.
Yeah. So does this mean that half is possible?
That's right. So the answer is, I'm going to, spoiler alert, the answer will turn out to be yes. And that's not my work, so that's going to be an older paper from 2012, which is beautiful, and I'm going to spend quite a bit of time on. And then I'm going to talk about two results which extend the 1/2 to harder versions of the problem. That's where we're going. So, okay. All right, so holy grail for the USM problem would be a 1/2 approximation. Unbelievably, this super basic problem was not sort of studied from an approximation perspective until a little over 10 years ago. So in addition to their negative result, the 1/2 barrier, Feiga, Marachny, and Vondrak did show a 2/5 approximation, a 0.4 approximation using sort of a noisy version of a local search algorithm. And then there were a couple papers that sort of, as often happens, right, more and more kind of bells and whistles and complexity gets added to the algorithm, and you do a little bit better. First it was a 0.41 approximation, a 0.42 approximation. So the trend didn't look very good. Looked like we'd need 200 pages to get a 1/2 approximation. But Buchbinder, Feldman, Naor, and Schwartz saved us all. And I guess partially atoned for their previous paper. And so they gave an optimal algorithm. It's a 1/2 approximation, right? So we know that's optimal. And moreover, and I'm going to show you the algorithm, I'm going to show you the proof. I think both are really from the book in the sense of Paul Erdos. So this showed up in FOCS 2012. It turned out I was actually the PC chair of FOCS 2012. I found it very striking at that time. I still find it striking now. So I'd say of the past decade, this is one of the main new algorithms from the book that I feel like I've seen. There's others, of course, but this would be one of the ones I would name as sort of most elegant algorithms of the last decade. And that's what I want to tell you about next. Okay? So the so-called double greedy algorithm, okay, of Buchbinder et al. All right? So this is going to give us a 1/2 approximation for USM. I'm going to phrase the analysis. The algorithm will be exactly as it is in their paper. I'm going to describe the analysis fairly differently than the way they describe it, and I'm going to do that so that we segue as easily as possible into the next thing I want to talk about, namely, which is online learning of submodular functions. Okay? All right. So, before we talk about the double greedy algorithm, it's probably worth saying, well, what's up with just the normal greedy algorithm? And in fact, if you only know a little bit about submodular functions, one thing you might know is that greedy algorithms often work really well. In fact, they're often optimal in submodular optimization. So what's the natural greedy algorithm? You start with the empty set. Okay, you look at which element would give you the highest marginal value, you add it, and now you just keep repeating. At some point, maybe all of the elements would give you negative marginal value. Remember, the function's non-monotone. And you stop if you get to a point where all of the remaining elements would cause negative increment. Okay?
How do I know what's the value of an element? I thought they can just query a set.
Yeah, so you'd query the singleton. Right, so you start with the empty set. And so you're maintaining a set in your mind, initially the empty set. And you're debating whether to add something into it or not.
Polynomial. It will be
exactly right.
Every time I add everything to S and C.
Exactly right.
It's a polynomial.
Exactly. Yeah, so you have a linear number of iterations, and there's a linear number of things to check that you might add at this point.
Okay.
Yeah, so it's going to give you a quadratic bound on queries. Yeah.
Okay.
But I glossed over that. Yeah. So this doesn't work. Okay, for the USM problem. Okay, it would work if you had a cut function or very special cases. It's not going to work in general. So here's a very simple example. Okay, here's a function. It's submodular, I promise. Easy for you to check at home if you want. Let's distinguish the first element of the universe. And let's say any subset which includes element number 1 has value 2. Okay, it doesn't matter if you only have element number 1 or if you have everything, it's going to be 2. If you exclude the first element, let's say it's just the linear function. So the value of the set is just the cardinality of the set. Okay? So what is greedy going to do? Well, greedy is going to think about adding the various elements, and it'll notice it gets the highest marginal value from element 1, a marginal value of 2. And once it's committed to having element 1, it's stuck with an objective function value of 2. But of course, if you just pick everything else, you'd have an objective function value of n minus 1. Okay, so no approximation whatsoever. You might notice that if you did a greedy algorithm in reverse, okay, if you started from everything and then deleted down, as long as it was helpful, in this sort of greedy way, that would work fine here. Right? Because you'd start with everything, it would have value 2, you'd try deleting anything from it, and you'd say, whoa, if I delete element number 1, my objective function jumps from 2 to n minus 1. Okay, so the reverse greedy algorithm would work. Could the reverse greedy algorithm work in general? Well, no, because there's a sort of symmetry to submodular functions, which is if you just always take the complement, you get another submodular function. So you apply that operation to this example to break the reverse greedy algorithm. Okay? So the big idea then of Buchbinder et al. So they have a big algorithmic idea and a big sort of analytical idea.
What about the maximum of the two?
Yeah, so I was actually just thinking about that. I think that doesn't work either, but I was not able to immediately come up with an example yesterday when I asked myself that question. Yeah. So we're going to do something a little more slick, a little more non-trivial than just taking the max of the two. And I'm pretty sure this is a bad example, but I have to check that. So the big idea is to actually sort of, in some sense, run the forward and greedy algorithms in parallel, using each to inform the decisions made by the other. Okay, so let me explain what I mean. So the algorithm is going to be underdetermined, but let me tell you sort of the basic thing. So it's going to do a single pass over the elements. So we take the universe and we order it arbitrarily, okay, adversarially if you like. We maintain two solutions. Okay, initially they're opposite extremes, the empty set and the full set. At the end of the algorithm, they will have converged into the same thing. Okay, so X is nothing, Y is everything initially. Now we go over the elements one at a time, and when we encounter element I, at that point we make an irrevocable decision about whether I is going to be in our output or not. Okay? And we're going to keep modifying x and y to respect our decisions. So if we make a decision to include element I, that gets inserted into x where it wasn't before. It was already in y, so it stays there. If we make a decision to exclude I, right, then we're still out of x. It wasn't in there in the first place, but we remove it from y. Okay, and that's the binary decision we're going to make each time we encounter an element. Okay?
How do we make?
Say it again?
How do we make?
You will say.
Yeah.
Okay, right, and so it's exactly right. It's underspecified because I have not told you how we're going to make the decision whether to include or whether to exclude. And in fact, I'm not going to tell you right now. I'm going to do the analysis, and from the analysis, it will become clear how we want to make this decision. Presumably, we will make the decision using the information of the marginal contributions of these two elements. Right? So we could define alpha I as like, well, if we did pick I, right, y will stay the same, so it doesn't change. X picks up I. How much better would x get if we added I? Alternatively, if we excluded I, we'd be removing it from y. How much better does y get by excluding I? Okay, so that's alpha and beta. Presumably, we'll use these to inform the decision of whether to include or exclude. Right? So the most simplest thing you could do is just whichever one was higher, you pick that. Okay, that would be one example of a greedy algorithm in this framework. We're going to wind up doing something a little bit more clever than that to get to the 1/2 approximation. Okay, but anyway, so that's the big algorithmic idea. Now I want to proceed to the analysis. Again, even though we don't have the algorithm, because the analysis will motivate the final algorithm. So what's the big analytic idea? Okay, well, it's basically kind of a very nice charging argument. Two things presumably we want to keep track of as the algorithm proceeds is the current value of the x solution and the current value of the y solution. So by x sub I just mean the current value of the set x after we've considered the first I elements. Okay? So that'll be some subset of the first I elements. This again is what the current status of y after I iterations. Okay? So that'll be sort of everything after I plus some subset of the first I elements. The same subset in both xi and yi. Okay? So presumably we want to track, so these are both, oh, I forgot to say this. Well, let me not go back. So in the USM problem, I said I wasn't going to promise that the function was non-negative, and I'm not. However, to get positive results, you need to assume that it's non-negative on the empty sets and on the full universe. Okay, so that assumption I will need. And actually, it's sort of the worst case for approximation for it to be equal to 0 on both the empty set and the full set. So for the rest of the talk, just imagine we have this non-monotone submodular function, 0 at nothing, 0 at everything, and possibly positive in between. Okay? Good. So, but the third thing, so there's two obvious things to track, but then we're also going to track how the value of opt changes over the course of the algorithm. Now I say that, and you're like, well, what do you mean? Opt is opt. It's not changing. But so here's what we're going to do. In our minds only, right? So just for the analysis, we're going to start from the optimal solution, and we're going to change it as needed to conform to the decisions that the algorithm has made. Okay? So in particular, after iteration 1, if we include 1, we're going to change opt to include 1 if it didn't already. Okay? And so on. So at the end of the algorithm, all three of these sets, whoops, let me just say that here. All three of these sets are going to be the same, just by definition. Okay? So for all of xi, yi, and opt I, by definition, they all agree on the first I elements. It's just whatever the decisions the algorithm made. Okay.
Right. So it's opt I, you take the optimal solution and then at the beginning and you modify it, or is it like after you pick 1, you look at the best thing containing 1?
The former one. So you,
okay.
So you take the so thanks for the clarifying question. You take the optimal one for the original function f.
Okay.
You hold the last n minus I elements fixed. They're just as they were before. And now you just change the first I so they're exactly what the algorithm did. Yeah.
Okay.
Yeah, thanks.
And you wrote it like this, using already the assumption that it's 0 on the empty set and on the whole set.
That's right, because otherwise you would care about the delta between this and f of the empty set. Absolutely right. Absolutely right. Yeah, so think of x and y starting at 0 and going up. Opt, as we modify it in this way, it started out being opt, so it's going to be getting worse. Okay, so x and y are getting better, opt is getting worse. We want to track all three of those evolutions. Okay? All right. So just to make sure this is clear what's going on, let's look at an example. Right, so we have 4 elements. So initially x has nothing, y has everything. Suppose opt has the first, second, and fourth elements. Remember what alpha and beta mean. Okay, that's basic. Alpha is the consequence for x if you add I. Beta is the consequence for y if you remove I. Okay? So what this means, this is saying that if we add element 1 to x, it will jump from 0 to 1. If we remove element 1 from y, it'll jump from 0 to 5. Okay? That's what that means. So then our algorithm makes a decision. Maybe it's greedy, and it just says, okay, well, let's actually do the +5. Let's remove, or let's sort of exclude item 1. So x stays the same. Y does indeed drop to 0 and y goes up to 5. Opt, notice, we're going to modify. Opt actually did include the first element. Our algorithm decided not to. So we have to modify opt by zeroing out its first coordinate. That's going to drop its objective function value, let's say, from 8 to 7. Okay? And then we continue. Okay, so we look at alpha and beta again. So this is telling us that if we add the second element to x, this will jump up to 1. If we remove the second element from y, this is going to drop from 5 to 4. Okay? So if again we're greedy and we decide to include the second element, right, that's what changes. Y stays the same, opt stays the same because opt had that element anyways. And then we continue. Okay, so element 3, this again would say including that, this would go from 1 to 4. Excluding that, this would go from 5 to 7. Okay, and so on. All right. So is everyone clear on this definition of x sub I, y sub I, and opt sub I? That's really important. Okay. And everyone sees they're going to converge by the end of the algorithm, just by definition. Okay. And then these are the numbers we're going to be tracking. Okay, the succession of numbers in the rightmost column.
Is this for any sequence? Like, we can look over the element in any order? Like, are they all going to
That's
be
right.
the same thing?
That's right. You can go over the elements in an adversarially chosen order.
Okay.
Yeah. So that turns out to not, which is sort of weird when you're thinking about the adaptive greedy algorithms, which usually work so well. But it turns out as long as you're tracking the forward and reverse at the same time, you can get away with an adversarial ordering. Yeah.
Wow.
Yeah, non-adaptive and everything. Yeah. Okay, good. So, as we discussed, they all coincide at termination. And so what's going to be the plan of the analysis? Again, it's going to be a charging argument. And so we want to track how much these are going up. And actually, we're going to track the average of how much these two things have gone up. Again, at the end of the algorithm, these will be the same. So it's really just the same as the value of either one. We're going to track how much worse opt got. Okay, our goal is to prove that the gain in the average of x and y is bounded above or can be charged against any loss in opt. Or sorry, the other way around. Any loss in opt can be charged against the gain in the average of the two algorithms. Okay? This would imply a 1/2 approximation. If you like, you can just sort of look at the algebra. So remember, x sub n, y sub n, and opt sub n, those are all the same. That's just the final output of the algorithm. So you collect those terms together, you get 2 times the algorithm solution, at least the optimal solution, or algorithm solution is at least half opt. Or if you kind of like to think more visually, imagine that sort of, like there's some value of opt and it's getting drained over the course of the algorithm. But then this is saying that actually the average value of x and y are going up at the same rate. Okay, so in the worst case, they meet in the middle at half of the original value of opt. Okay? So this is going to be the goal. We will prove this. Right? So that's where the 1/2 approximation is going to come from. Okay? All right. So how do we prove it? We're going to prove it in the simplest way you might hope, which is iteration by iteration. Okay? It's going to be a randomized algorithm, so these inequalities will hold an expectation. Okay? This is what we had on the last slide. This implies the 1/2 approximation. A sufficient condition would be to show that just the terms involved in iteration I, the analogous thing holds. So in a given I, we look at the average gain by x and y, okay, in iteration I, and we look at the degradation in opt at iteration I. Okay, and we're going to prove that this holds in iteration by iteration. Okay. Okay, good. So sorry, let me just, so we need to understand this. So we will prove this. We need to understand what are these 3 differences going to be in the various cases. Okay, so that's going to be the next slide. Everything I'm going to say in the next slide is sort of dirt simple, but it's going to add up. So add questions as they come up, okay, because there's kind of going to be a lot of data at the end of the day on this slide. So how do these things change? How does the value of x change? How does the value of y change? How does the value of opt sub I change? Let's start with x. Pretty simple. Remember the notation. Alpha I is just how much x gains by adding I. Beta I is how much y gains by removing I. So by definition, right, what happens with x, either it stays exactly the same if the algorithm doesn't choose element I, or it goes up by what we said it went up by, alpha sub I. Same thing with y. Okay? So either it doesn't change, that's if we choose to include the element in the algorithm, or if we exclude it, then we get the gain that we said we got, beta sub I. Okay? Now, quick lemma, and the first place that submodularity shows up in this talk. Alpha could be negative, beta could be negative, but they can't both be negative. Okay? Alpha plus beta has to be non-negative. And this follows from submodularity. Okay? Why? Well, suppose like beta I was negative, right? That would mean by excluding I from y, it harms you. Okay? Or put differently, if you put it back in, it would help you. But it's going to help you even more with respect to the smaller set, xi minus 1. Okay? So the gain alpha to x is going to be at most the harm minus beta that you get for y. Okay? So now we're just going to forget the proof, and we're just going to remember submodularity implies alpha I plus beta I is non-negative. We will use that. That will be important. Okay? All right, good. So from the algorithm side, we sort of know what's up. Okay? We can either pick I, we get the alpha, or we can exclude I, we get the beta. What's up with opts? And we know one of the options is good. One of the options at least will give us a non-negative amount. All right, so for opt, which of course we don't know, but we can think through the various cases, a couple things could happen. Okay? One, we could get lucky. Lucky means that our algorithm happens to do the same thing opt did on this particular element. It's in opt and we picked it, or it's not in opt and we excluded it. Okay? Then opt I and opt I minus 1 are the same. No changes. Gain is 0. If we're unlucky, we do the opposite of opt. Okay? So for example, maybe I is supposed to be in the optimal solution. It rightfully belongs there, but our algorithm unfortunately excluded it. Okay? But we get a bound on how bad opt could be harmed using the same style of submodularity arguments. Right? So what does it mean if alpha I, dropped? That means that when we remove I from opt, there's some harm. Okay? So if we put it back in, there's some gain. But again, the gain would only be bigger if we added it to the smaller set xi minus 1. Okay? And that was exactly alpha. So alpha was the thought experiment. What if we add I to xi minus 1? What is the consequence for opt? It's that same marginal value with respect to a bigger set. Okay? All right. And then the symmetric deal with the other way we can make a mistake. Okay? So if I rightfully belongs outside of opt, but we actually include it, then again, by the submodularity, the cost to us is going to be at most beta sub I. Okay? So let's take stock of where we are. So what's the takeaway from this slide? Okay, so really, I want you to start thinking about the algorithm as playing a game against some adversary. Okay? So the algorithm is deciding whether to include or to exclude, and the adversary is deciding a few things. It's deciding alpha and beta, perhaps, but it's also deciding whether or not I is an opt or not. Okay? So what are your payoffs in this game as the algorithm? Well, here your payoffs are clear, right? So if you include it, you get payoff of alpha I. If you exclude it, you get a payoff of beta sub I. Okay, and you can choose. Whichever one of these you want to do, go ahead and do it. Down here, we don't know. Okay, it depends on opt, which we will never know. If we include, okay, we will either have no consequence or we'll have a consequence of beta sub I. Okay, so we pick up alpha sub I in x, but we have a degradation of beta in opt. Symmetric case in the excluded way. Okay, so either we get lucky and there's no consequence, or we get a consequence of alpha when our gain was beta. Okay? So that's what we've got going for us. Right? We can pick alpha or beta. Then as far as the consequences for opt, it's either beta or alpha if we're unlucky, or 0 and 0 if we're lucky. Okay? So that's going to be the game I want you to think about. All right, and remember that alpha plus beta is non-negative. Okay? Good. So what were we going to prove? This is what we're supposed to prove. Okay, this is just the same thing I had a couple slides ago. This is just the iteration by iteration version of the charging argument we want to do. Okay? So our algorithm, right, it gets to choose a mixed strategy in general over inclusion and exclusion. It could do something simple like greedy, or it could do something, it could flip a coin. So think about a mixed strategy P comma Q. P the probability of including I, Q the probability of excluding I. P and Q, the algorithm can compute with knowledge of alpha and beta. Right? The first thing you do in the algorithm is you compute alpha and beta, and then you decide how to randomize. So P and Q can depend on alpha and beta, but they cannot, of course, depend on opt, which the algorithm doesn't know. So then the question is, why don't we just kind of do a min-max type approach, and let's just hedge, pick our mixed strategy, so that no matter what's going on in the optimal solution, whether i's there or not, we can actually push through this iteration by iteration bound. So what does that mean? So it means we want to pick a mixed strategy PQ so that our gain, so the gain in x and y, or rather the average gain in x and y, what's that? Well, with probability P we include, in that case we get a payoff of alpha sub I. Probability Q we exclude, in that case we get a probability of beta sub I. So this is just the expected rise in this stuff for the mixed strategy P comma Q. What happens on this side? Well, if I is an opt, then our mistake would be in excluding it. So that happens with probability Q. And remember, in that case, we can bound the gain by alpha sub I, by submodularity. Symmetrically, when I is not an opt, the mistake is when we include. That's why there's a P sub there times beta sub I. Okay? So in other words, what I'm trying to say is, if we can find a P and Q with this property, then we are done. Okay?
So what are the P and Q? Q are 1 minus P?
Correct.
Oh, okay.
Yeah. 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 You know,
Okay.
over-parameterized model.
Yeah, I like it when you have.
Yeah. Okay. Yeah. P and Q are non-negative and sum to 1. Okay. Good. So now the $64,000 question is, does such a P and Q exist? And that, of course, is an exercise any of us could do on the back of an envelope. And the answer is yes. Okay. 2 easy cases. So first of all, if one of the alpha or beta is non-positive, so if it's a bad idea to include I in x, if it actually gets worse, or if it's a bad idea to exclude I from y, if it would actually get worse, then don't do it. Do the other thing. Okay? So if it's bad, if you know excluding would harm y, then just deterministically add the element, and so on if alpha's non-positive. Don't forget, alpha and beta cannot both be negative. Okay, so there's no worry about being well defined here. Okay, and then you can just check, right? So that these would zero out the right-hand side, but you get something non-negative on the left-hand side. Otherwise, you can use a mixed strategy. Again, remember, it can depend on alpha and beta. Right? We're told alpha and beta, then we pick P and Q, then it's unveiled to us whether I was an opt or not. That's kind of the sequence of events. And it turns out to be very natural what to use. You just do it proportional. Okay? So both alpha and beta are positive. They both look like a good idea. Then you just randomly choose the one proportional to the gain that you would get. Okay? So if one would gain 7, one would gain 3, you're going to do a 70-30 split between including or excluding. And that's the randomization in the algorithm.
So why do we have randomization? Because we assume that we have an adversary?
Yeah, so basically we need to hedge between these two universes that we can't, two scenarios we can't distinguish. Whether I is an opt or whether I is not opt. Like, we'd love to be able to just guess. We'd love to just know whether I is an opt or not, because then we would just copy opt,
Okay,
basically.
because we assume that the optimal is, there's, okay.
Yeah, so it's basically, one way to think about it, it's the reason you randomize in like a min-max strategy.
Yeah.
Right, so we don't know what's up with the optimum. We're sort of thinking of it as if it's almost decided after all of our coin flips. So we want to do something which is good no matter how things turn out in the optimal solution. Another way to think about it, if we go back to this summary slide, so there's a tension between two different things. On the one hand, high alphas and betas are good. So on the one hand, you want to make algorithmic decisions which are sort of greedy, like if alpha is big, you want that. If beta is big, you want that. On the other hand, you also want to take into advantage the possibility that you do luckily guess exactly what opt did, and then you don't have this harm on the third term. So we're exactly hedging between these two things. Okay, on the one hand, we want to respect the gain we're going to get. On the other hand, we do want to have some chance of getting lucky and missing whatever the adversary did.
Yes, I'm asking, do we know that it needs to be randomized?
In fact, it is known that it does not need to be randomized. In the sense that there's a de-randomization by the same authors or maybe a subset of them of this algorithm. Now, if you want to do it in this sort of simple single pass, just make irrevocable decisions framework, then you can show that if you're greedy, so if you sort of ignore this and you just say pick whichever of alpha or beta is higher, you get a 1/3 approximation, and that's tight. Okay, so within this sort of framework, you need to do the randomization to do the hedging.
What happens if you just flip a coin? So the expected gain in the listen the expected gain in the left, alpha I plus beta I over 2, and the expected loss in the right also, like in most, alpha I plus beta I over 2, or
So you're saying a fair coin?
yeah.
Yeah, I think.
What happened?
So a couple of things. So one is just what's true, and what's true is that you get a 1/4 approximation.
Oh, okay.
Yeah. If you just pick a uniform random subset of the universe. And that wasn't known actually until that Feiger-Marachny-Vondrak paper.
Picking a fair coin means that you don't do anything. You choose a random set, right?
Exactly. Exactly right. Exactly right.
You don't pay, so you expect to do right?
Yeah, but you get something which is maybe surprising. So you get a 1/4 approximation, which again is tight for a random set.
Random set gives you 1/4.
A random set gives you a 1/4 already. Yeah, so somehow you have to, this is one of those things where really you have to pursue optimality to kind of get the most interesting algorithms. So, but that's good, because sometimes you pursue optimality and, you know.
Done. You just say it's a constant. Okay, done.
You take 2 randoms.
Oh, seriously, if you glue them somehow, it's gonna...
Well, so I would almost say, I would almost think this algorithm justifies our obsession with optimal constant factors, right? So like it'll lead us to like a really cool algorithm.
So
right?
Tim,
Yeah.
so in this paper, did they get 0.4? What do you have to do to get a crazy number?
You have to write a really long proof.
I tell you what, they had the whole thing. Now you don't want to get a few papers out of it.
Now the 0.41 and 0.42 were different sets of authors, I should say. So yeah.
So a random set gives you a 1/4, and there are examples where with very high probability you get close to a...
That is a good
What if you
question.
take 100 random things and you take the maximum?
Yeah.
Yeah. I don't recall. I'm going to, I would imagine, I'm skeptical that could work, but I cannot remember an example or a citation.
Well, maybe
So
we get stuck in some maximum, in some local maximum, minimum.
I mean, max cut indeed.
How about just distance from the middle? Wait, no, how about just distance from the middle one?
So I sort of, maybe I'll say the one, so as far as the lower bound side, I do remember a little bit of the 1/2 lower bound, which is basically you can concoct a submodular function that almost everywhere, it looks like the cut function of a complete graph. And the cut function of a complete graph, you're only going to cut half of the edges. But if you sort of guess a random bisection, then it's going to suddenly start looking like the cut function of a complete bipartite graph, okay, giving you double the amount of edges. Okay. Now you have to sort of work to stitch these together, preserving submodularity, but that's why you can't do better than a half using any algorithm with a polynomial number of value queries. The 1/3 example for deterministic, I don't remember off the top of my head. I'd have to check. Okay, okay. Good. Oh, yeah, so let's see, we finished? We finished. Right, so if you pick proportional, again, then you can just check, right? So on the left-hand side, you get the average of the sum of squares, and the right-hand side, you get their product. Complete the square, that's non-negative, and we're good. Just to make sure, all right, so now we actually have the algorithm. Okay, so this slide actually states the algorithm in case you lost the forest for the trees. Single pass over the elements, arbitrary order, alpha and beta. You just say what would be the consequence for x or y if we include or exclude. If one of them is a bad idea, you don't do it. Okay, so if beta is negative, you always include. If alpha is negative, you always include. Otherwise, you do it proportional. Okay, and again, the theorem by Buchbinder, Feldman, Moran, and Schwartz is that this is an optimal 1/2 approximation in expectation.
It sounds a little bit like simulated annealing.
That is actually what the 0.41 is.
Oh, okay.
What
Simulated annealing, yeah. Yeah, so, yeah. Okay, good. Now, I also want to remind you the key step in the analysis, okay? So an adversary chooses alpha and beta as a function of alpha, and they have to sum to something non-negative. As a function of alpha and beta, you get to choose P and Q, okay? And you need to satisfy this inequality, right? So you need to basically, your expected payoff has to sort of beat, kind of the worst case over whether I is in or outside of opt. Okay? Okay, once we had this, so this is what we exhibited the mixed strategy to prove. Once we had this, we could prove the iteration by iteration bound. We sum over the iterations, and that gave us the 1/2 approximation. So this was the key inequality. And I'm highlighting this because this is what we're going to need to generalize. This is the key ingredient that we need to generalize to the online setting. Okay, so I've rephrased the entire analysis so that this is where we end up. All right? Okay, and that is the Buchbinder et al. Algorithm. Any questions?
It's good to give their first names because the last names are common too.
That's a good point. So Niv Buchbinder, Moran Feldman, I believe, Sefi Naor, and Roy Schwartz. Okay. Do I get a... I pass?
Pronunciation.
Say it again?
I love it when Americans need to, well,
Yeah.
but when people have to pronounce Hebrew names.
Yeah. I do what I can.
It's my life, right?
All right, any questions about, so I have to say, I mean, I'm going to go on and talk about, some work that I've done, but if really the main thing you take away from this talk is an appreciation and understanding of this algorithm, I hope this will, then I think I will view this as time well spent, frankly. Okay, but now I want to push on to generalizations, unless there are questions. Okay, so I may only have time for the first result, we'll see, which is going to be about online learning of submodular functions. So before I sort of talk about that, let me tell you about a broader research agenda, about translating good offline, computationally efficient offline algorithms to computationally efficient online algorithms. All right, so offline, what do I mean? Okay, so here's the abstract setting. So there's a decision maker and there's some finite set of actions. Okay, for us, the actions are going to be subsets of some ground set at the end of the day. An adversary at each time step, an adversary is going to give you a collection of capital T payoff vectors, okay, which just says as a function of your action what reward you reap. For us, these are going to be defined by submodular functions, okay? And for now, let's just assume that they're bounded, say by scaling between 0 and 1, okay? By the offline problem, I mean given these payoff vectors, find the action which maximizes the reward, okay, the cumulative reward, or if you like, the average reward over the given capital T payoff vectors. So that's what I mean by the offline problem.
So there are times, what are the T's?
Yeah, sorry, that'll be on the next slide. For the moment, I just give you a collection of payoff vectors, okay? I mean, if you interpret this in USM, it's a little weird because, I mean, basically you just sum up the capital T functions, you get another submodular function, but it'll make sense in the next slide. So the offline problem is just to give you a collection of reward vectors. You want to find the action minimizing average reward across those reward vectors. The online version, you have to make decisions irrevocably at each of a number of time steps. Let's say capital T time steps for a known time horizon capital T. You, before knowing what the reward function is going to be at this time step, have to decide on a mixed strategy, okay, distribution over all of your actions. So again, for us, that will be a distribution over sets. As a function of your distribution, but not your coin flips, an adversary will then choose a reward function, okay? Nature will then sample an action from the distribution that you chose, and you will earn whatever reward that sampled action gets on the adversary's, for the adversary's reward function, okay? So that's online learning, sort of very abstractly. And the usual goal in online learning is to get a no-regret algorithm, or a vanishing regret algorithm, meaning that over time, for a sufficiently long time horizon, you would like the average reward earned by your algorithm to be almost as good as the best fixed action in hindsight. Okay? So that's what this says. This is the best fixed action in hindsight. Okay? Notice this is identical to the definition of the offline problem. Okay? Computing this is the offline problem. This is the reward reaped by an algorithm that takes these actions to the different time steps. Okay? So you would like this to be as close to 0 as possible. Okay? So that's what I mean by online learning. Now, if you don't care about computational efficiency, there are no-regret algorithms that work quite generally. In fact, as long as you have a so-called exact best response oracle, so if I give you an exact solution, an algorithm that solves the offline problem exactly, then using follow the regularized leader, algorithms of that form, you can actually get no regrets, okay, efficiently with respect to the oracle. However, when you have hard problems like USM, like we're talking about, in general, you might only have an approximation oracle for the offline problem. And in the online version of the world, the natural goal is to get what I'm going to call lambda regrets. So here we want to do well with respect to a weaker benchmark. We're going to take the best action in hindsight and scale down its average reward by some factor lambda. Okay, multiply it by lambda. All right, think of lambda as like a half, for example. Okay, so that's what I mean by lambda regrets. Okay? And a general research question that I find very interesting is, to what extent good approximation algorithms can be translated into good online algorithms? Okay? So in other words, suppose I gave you, for the offline problem, a polynomial time or polynomial query alpha approximation algorithm, okay, for the offline problem. What we'd love is we'd love to have some general box to run this offline algorithm through, something that uses it in a generic way and gets an online algorithm with vanishing alpha regret for that same alpha. Okay? That would be really nice. Generic translation from offline algorithms to online algorithms. Let me mention one reason it's nice is because the online problem can only be harder. Okay? So the reduction in the reverse, there is a reduction in the reverse direction. If you give me an online algorithm with vanishing alpha regret, I can extract from it an efficient alpha approximation algorithm for the offline problem. Okay? So the best case scenario is to get vanishing alpha regret for whatever alpha you're able to get with the offline problem, and the question is, when is that possible?
Can you say, for example, what's the online and offline for the cut problem?
Sure. So, yeah, good. So the offline problem would be basically I give you a bunch of graphs all in the same vertex set. A bunch of graphs all in the same vertex set. You want to pick a subset of vertices, maximizing the average number of boundary edges across all of the graphs.
So it's the average performance of the set.
Exactly. Exactly.
Okay, so you take many copies. This is the time. Okay, I see.
Oh,
Copies of the same.
you're proving the reduction. Yeah, exactly. Yeah, absolutely right. That's why that's true.
And the online is you see every graph as a
The online is
every day you get-
day one. I show you nothing. I just tell you what the vertex set is, and you say vertices 3, 7, and 10, and then I show you the graph, and you're like, okay, now I see how I did. And then day two, you pick whatever subset you want. I show you a new graph, and we see how you did. Right, so it seems very unfair, right? Because I get to pick the graph after I see your distribution over action. So first of all, you need randomization. But even then, it still seems pretty unfair. And that's exactly why in online learning you focus on regret minimization. So a very sort of clever choice in the modeling in online learning is the benchmark is merely the best fixed action in hindsight. Okay? So your algorithm is only declared to be, bad if you missed out that there was some awesome action the whole time you should have just been taking. Okay? We at least want an algorithm that does not get, that does not miss out on some, always good action.
So you every day you come up with a new set, and the performance is considered for the new graph.
Yeah.
And you take the average of all the sets versus the graphs.
Right. So your algorithm will be picking different vertex subsets on different days.
Yeah.
Okay. So it'll do whatever it does. It has 12 boundary edges on day 1, 17 on day 2, whatever. You average that. That's how well the algorithm did. And now, once you've seen all of the graphs, in hindsight, you look backward, and you say, okay, if I had to pick the same set and use across all capital T graphs, which would be the best set to do? Okay, this obviously was an option for your algorithm to always pick the best set. It just didn't know what it was. But you'd like to say over time, it sort of figures out, if it either it identifies the best set or it gets performance comparable to the best fixed set anyways. That's sort of the regret minimization philosophy.
So what access do you have to PyT? Do you still have black box access?
That's a good question. Yeah, so for us, I'm interested in the specific instantiation where it's the USM problem, in which case this will again be a submodular function with value query access. I should say not much changes if you look at succinctly described classes of submodular evaluation functions. You have to work harder on the lower bound side, but Dobzhinsky and Vondrak, for example, have basically said the information theoretic lower bounds for the black box model hold also for natural succinct classes of submodular functions.
But of course, all these online, all these expert algorithms work even without assuming anything.
Exactly. Excellent point. Right. So let me get to that. So to what extent can you have translations of this form? Okay. And again, if you care about so the question was, what about something like multiplicative weights, which gets no regret under no assumptions? Okay. So I'm interested in computationally efficient learning algorithms. Now, is multiplicative weights computationally efficient? Well, it depends. Okay, the running time is linear in the number of actions. So it depends on what your action set is like. Think about USM, where actions correspond to subsets, okay, of a universe of size n. n is the natural parameter. The action set has size exponential in n. So a naive use of multiplicative weights would not be computationally efficient. Okay? But absolutely, if you have a sort of explicit action set, then there's not a hard problem here. Okay? All right.
If you can run multiplicative weights implicitly, then you can get, so if your optimization algorithm can sample from the expert somehow.
That's right. Yeah, and indeed, so that would be the dream of what this might look like. So could you generically kind of have an implicit implementation of multiplicative weights? And the positive results in this part of the world are often, basically taking follow the perturbed leader, which was originally developed kind of just for finite action sets, and basically showing how you could more or less implicitly implement that in different settings.
If your approximation algorithm, for example, is simulated annealing, then you can hope that it will just combine. Kind of exponential.
I see what you're saying. Oh, interesting. Interesting. So you're saying those, right, so I mean, definitely, so I'm going to think a great open question would be define a property of algorithms so that you have at least a translation for that family of algorithms. I would love to see a theorem of that form. Yeah. Okay, so could you always have the best case scenario? Could it be that the online problem is never harder than the offline problem? So no, we know that that's not true. Actually, from a paper here at Princeton, Alaa Hazan and Tomer Koren, they gave a fairly contrived problem showing that even if I give you an exact oracle for the offline problem, you don't have any so-called oracle efficient online algorithms. On the other hand, there's been some nice positive results. The nicest one is for linear optimization problems. Okay? So even if you have an exponential size action set, as long as your reward functions are linear, then this is a tricky result, but you can take any alpha approximation algorithm and get vanishing alpha regret. Okay, that's an important result by Kakade, Kalai, and Legev. Okay? What about other problems? Well, beyond linear problems, all we have is some scattered understanding. Okay, we have a number of specific examples where we can get these translations, but we really don't know any generic positive results beyond the linear case. Okay, and an open question is, is there a natural problem where you have a provable separation? Okay, where actually the online problem is strictly harder. You cannot recover the alpha that you got in the offline case. Again, we have a contrived problem for which this is true, but we don't have a natural problem. And when Josh and I started working on this, we were actually wondering if unconstrained submodular maximization would be a perfect candidate for such a separation. Okay, because the action set is exponential size as it has to be, and the reward functions are nonlinear as they have to be. Okay? So that was our starting point. We were sort of wondering, we were on the fence of whether we thought there'd be a separation or not. Turns out there's not. Okay? And that's probably the last result I'm going to have time to tell you about. Okay? Oops. So let's instantiate the generic online learning framework to the USM problem. Okay, so again, things unfold over time. Our action set are subsets of a known universe. Every time step, our algorithm is responsible for picking a distribution over sets. Given our distribution, an adversary settles on a submodular function. Then the action gets realized. And we want to have small lambda regret. Meaning, so this is the average performance of our algorithm over time. And this is the average performance of the best fixed set in hindsight. And because of the negative results, we're going to have to weaken this benchmark by multiplying this by a factor less than 1. Okay, by that 1/2 lower bound for the offline problem and the reverse reduction I mentioned, the best case scenario would be an algorithm with vanishing lambda regret for lambda equal 1/2. Okay, and that is indeed the main result of this paper. Okay. So how's it going to work? Let me tell you a little bit about the algorithm, a little bit about the analysis, and I've sort of done everything in the earlier parts of the talk to make this hopefully as painless as possible. So we're going to exploit both the algorithm and the analysis in the Buchbinder et al. Analysis. So this will be very much not a black box translation, as you'll see. Okay? So how do we exploit the algorithm? Well, we're going to use its sequential nature. Okay, remember, it makes a single pass over the elements in some order from 1 up to n, decides whether to include or to exclude. Okay? So we're going to run n different online algorithms. Okay? Each online learning algorithm A sub I responsible for deciding whether I should be included or excluded. Okay? So we're going to have n online learning algorithms running in parallel, each monitoring a set of only 2 actions, in or out. Okay? Now, how's it going to work? So, it's going to have these online learning algorithms. At a given time step, we're just going to ask the n algorithms, what should we do? And each of the n algorithms will come back with an include or exclude decision. That'll be our set for today. Okay? Then we find out the submodular function. Okay? At that point, we want to give feedback back to our n different online learning algorithms. And the feedback we give them are the alphas and the betas. Okay? We say, well, now that time step t is finished and the dust has settled, we look back and we say, given what the function wound up being, and given what the I-1 sort of algorithms before you decided to do, what would have been the gain at that point of you including or excluding the alpha and beta? Okay? So you give this feedback back to each of the n algorithms that you're running. Okay? Say it again?
What is the feedback?
Uh,
Is it like only for the ith time step, or do you combine all the
So every time step you're going to get feedback.
Okay.
So every time step, you make a decision, the adversary makes a move, and then you get the feedback. Okay? And so here we're sort of we're designing this kind of master meta algorithm, which is coordinating these n different binary action algorithms. And the question is, how does the meta algorithm pass feedback down to kind of the soldiers, if you will, okay, the 2 action setting. And so what we're going to do is we're just going to say what would have been the consequence of you including or excluding. And at the time that we are giving you that feedback, we know what the function was at time t, and we also know what the first I-1 experts did at time t. So I can tell you your alpha, I can tell you your beta.
This will be used in t+1 step though.
Yes, so at all times, right, so exactly. So you do not know alpha and beta when you're making a decision at time t. You do know the alpha and betas from the first t-1 time steps. And that's exactly what an online learning algorithm is. So you use the past, first t-1 time steps only to make a decision at time t. Yeah. Okay, so that's the high-level idea of the algorithm. So in a little more detail, right, so we need to instantiate what these sort of binary action algorithms actually do, but we're going to have one for each element.
What is it? So the online here is just a 1 up to n, or a...
Good, okay.
Do many...
Good.
Because you said many graphs and many cards. This does not correspond to giving...
Yeah, so the online part is over time. So this universe is fixed once and for all. I tell you at the beginning, the universe is 1 up to n. Now, at each time step, so then there's going to be these time steps. There's going to be a new function at each time step. Within a time step, you do a pass over the elements, but that's just your algorithm. You knew they were all there. You could have done something more complicated. We're just going to do something simple within a time step.
Yeah. Yeah. So the online part is just the many instances.
Exactly right.
Right.
Exactly right.
Okay.
Yeah. So each instance you are given whole at the same time. Yeah. Yeah. Okay. Good. So you asked the opinion of your expert algorithms. Should I include? Should I exclude? They tell you, and then you give them the feedback that we said. Okay. This again is underspecified because I haven't told you what these AIs are doing. Okay. All right. So let me remind you what was the key lemma in the offline analysis. Right. So we had this mixed strategy. So in the offline analysis, I tell you alpha and beta. And then as a function of alpha and beta, you get to pick P and Q so that you can hedge your bets appropriately. Okay? This was the key lemma in the offline analysis. Now, I structured that analysis so that when we pass to the online setting, all we need is the analog of that exact same lemma. Okay? So there's 2 differences. The trivial difference is now that we're going to have a sum over t, okay, instead of just one fixed instance, but whatever. The one that's non-trivial is now the P and Q that we choose at time t cannot depend on the alpha and beta at time t. We don't know those yet. We did in the offline problem, we do not in the online problem. So the P's and the Q's are decided purely as a function of the alphas and betas you got from the first t-1 time steps. Okay? So that's what this says. The analogous lemma, we have sums over t's, and with the understanding that P's and Q's at time t depend only on the first t-1 alphas and betas. Okay? If we can prove this lemma by the exact same argument we used in the offline case, we'll be done. Okay, we'll have a vanishing 1/2 regret algorithm for the online setting, if we can prove this lemma. Okay? All right, I am out of time. Okay, so how do we prove it? We prove it using Blackwell approachability. Which is sort of an analog of von Neumann's min-max theorem, but for vector-valued payoffs. So
We cannot do here exponential weights because you can approximate. I mean, the number of possibilities for P and Q. I can go by jumps of epsilon if I'm allowed to. Use
oh, right. Oh, sorry. Yeah. Thank you for saying this. This was a comment I wanted to make. So so this is what we want to prove, and I haven't told you what our binary action online algorithms are yet. And a very natural first thought would be, why don't we just stick in any off-the-shelf, no-regret algorithm, okay, like exponential weights or multiplicative weights, whatever you want to call it. You could do that. You will not get vanishing 1/2 regret. Turns out you will get vanishing 1/3 regret. And the reason is that, while this sort of looks like, the lemma you're trying to prove, it kind of, looks like the best fixed action in hindsight. That's actually, if you think about it a little bit more carefully, that's not what this is saying. Because there's sort of two things going on. One, is you're picking either include or exclude. That's your action set. On the other hand, the adversary is picking, is I in or is I out of the optimal solution. Okay, so there's really kind of two different benchmarks you're trying to track simultaneously. And then also just kind of, as far as the nuts and bolts, I mean, just the payoff structure is not correct, right? So basically, if you just cared about a fixed action, that would be the sum of the alphas. Here would be the betas, and here you have the q's mixed with the alphas and the p's mixed with the betas. So it's not, syntactically it looks a little like, an off-the-shelf no-regret algorithm should get you this, but it doesn't. So we actually do need some kind of bespoke algorithm, subroutine, to plug into the two-action expert problem, okay? That's why we go through the Blackwell approachability approach. So basically I don't have time for this, but just intuitively, why would vector-valued payoffs in games ever come up? Basically because we're trying to have our cake and eat it too in this lemma. We're trying to say, okay, well, on the one hand, we have the payoff if, that we get if I happens to be in the optimal solution. On the other hand, there's the payoff we would get if it's not. So you can think of that as like a pair of payoffs. Okay, so that's the game that we look at, is where pairs of payoffs correspond to how well you're doing with respect to the two benchmarks. Blackwell approachability is a tool for playing games so that you do well simultaneously across multiple criteria. So that turns out to be the perfect fit for what to do here. And that is what proves this final lemma and gives the online result, vanishing 1/2 regret. Okay. Good. So that's what we proved. That's the algorithm. That's the guarantee. I'm going to skip this part. This is when I said we did look at one other lattice, and specifically there's a natural continuous notion of submodularity on hypercubes, which is strictly harder, or which can only be harder than the USM problem that we already looked at. And so we got the first 1/2 approximation algorithm also for maximizing a submodular continuous function over box constraints. Okay? And this uses the same Blackwell approachability approach, but is sort of more complicated for various reasons. Open questions. I already emphasized the offline to online translations part. I really think there's, I would bet there's some really cool theorems to be proved in that direction. I think that could be a really good, project for someone to work on. So that's kind of a general research direction. Our continuous result, it's only for box constraints. You'd be interested in optimizing over other feasible regions as well. And just, again, to prove the point that there are still very basic questions in submodular optimization where the approximation threshold is unknown, I offer you maximizing a monotone continuous submodular function over a simplex, where the open question is, can you or can you not get 1 minus 1 over e? So sorry for running out of time, but I'll stop here. Thanks.